Welcome to the podcast called What's Under the Hood. The whole concept originated because I was inspired by the idea that some people they use kind of a car analogy. And I thought that the general public, but even more so people that are on the fence about nuclear energy, they would be able to benefit, especially ones that are students or learning about the how they function and what's coming up, how the industry is changing. So I've got Azrudi Mustapha, and he's actually connecting from Malaysia, and he's going to tell you how some of his background, and he's got his own design of a reactor that is at this stage is it's not, they haven't built anything yet, but he's got a model, he's got diagrams, he's got quite a fascinating reactor that he worked on when he was in the UK, and he's going to tell you about that. So welcome, Azrudi.
And thank you very much for the warm welcome. Thank you.
Okay. And so give us some background. First of all, maybe where you grew up, how you ended up going to the UK, why you're back in Malaysia, that kind of thing.
Yeah, sure. Well, it's quite a long story, so I'll try to keep it compressed. Okay. First of all, thanks for having me on this podcast. And it might be of note that we are actually 12 hours difference between us. So it's and that means you're exactly on the other side of the planet. And it's impressive that we can do this today. We wouldn't have been able to do this like 20 years ago. So that's really quite impressive. So my background, let's see. Well, I was born, I was raised in Malaysia. I've always been raised in Malaysia. But when I did my bachelor's degree, I got this opportunity to work in oil and gas because Malaysia is an oil and gas exporting nation. I got this scholarship from our national national gas company. But they offered me 4 years to do it in 2 years to do it in Malaysia, 2 years to do it overseas, and I got another offer to study electrical engineering in Canada, and that was 4 years in Canada. So, I was like 18.
Really?
And my decision making was really simple. So I was like, I'd rather have 4 years experience in Canada. So I didn't care about the industry. I just cared about how long I get to travel, like to explore other cultures. So I chose Canada, and I did electrical engineering. So electrical engineering, I discounted the complexity of the power sector in the past. But now, as you can see, everybody's talking about sustainability. Everybody's talking about green energy, about how advanced civilizations, that's directly correlates to energy consumption of those countries. So I think in hindsight, I kind of make the right choice. This is where my passion is. I wouldn't have been able to see myself working in the oil and gas industry, but the energy sector, the electricity, the electrical power sector, that's really where my heart is. And so I grew up in Malaysia. I went to do my bachelor's degree in Canada in the power systems electrical engineering. And when I came back, because the people who sponsored me to do this study, they are the utility, the electrical utility. We have one vertically integrated utility in Malaysia. So everybody who works in the power sector would probably have been engaged with this company. So I worked in this company. I worked with servicing the grid, the electrical grid, the power grid. And during my time there, I was also tasked to look at alternative energy, and in Malaysia.
Was that Ontario, by the way?
Was that yeah, it was in Ontario. My university was Carleton University in Ottawa.
Yeah, okay, good.
Yeah, it was great. I love my experience there. I love the canal. I love the how they froze the canal in the winter, and you can go through town just. Oh no, I wanted to, but at the time I wasn't involved in the nuclear sector or in the power sector. I was just a student. I was just exploring I was just exploring this country, Canada. I did not know. Looking back now, I kind of missed out on a lot, but I wouldn't have had that kind of interest back then when I was younger.
Okay.
So yeah.
How many years ago was that?
Oh, that was a long time ago. That was like 20 years ago now. And
okay.
Yeah, slightly over, so that will reveal how old I am. So, but we did take lots of road trips. We drove all the way to Florida. We drove all the way to Halifax just by car without GPS, all just using those normal maps, right? Just
Right.
and yeah, I enjoyed that experience. Really, I really, really enjoyed that experience
And then
of seeing Canada.
what brought you to nuclear then?
Right. So when I was working with the utility, I was one part of the job was to look at alternative energy. So my job was basically ensure all customers get their power. We want to minimize breakdown. So the mantra is no breakdowns. So but if you have to have a breakdown, reduce the duration of a breakdown as much as possible. So part of the job, because in Malaysia you have the city center and then you have the rural areas. So some of these rural areas you still have to commit to ensuring they have backup supply. But the grid wasn't as developed in the rural areas as in the urban areas.
Mhm.
So, but there was this opportunity to look at mini hydros. So that's hydropower, but generated by rivers, not by the giant lakes, but just rivers. But because rivers are seasonal, sometimes we get a lot of rain and we have a lot of flow. Sometimes we don't have rain and we don't get the flow. So those hydroelectric plants, hydroelectric plants, they cannot guarantee me that I'll be able to supply a factory with power.
Oh,
Meaning, even though I can get the juice from there, but they're not reliable. So I still have to plan for another substation, meaning to extend the grid to
okay.
develop second lines to these factories. So in that period, I learned that yeah, hydro is great, but but if a factory loses their power supply because they're waiting for the hydro to go back up again, that's a loss of business. That's a lot of, like, if a factory is pulling cables in spools, like large cables, they're pulling in spools,
Yeah.
and they're trying to put 100 meters on a spool, for example. um, but they lose power when they've already spooled 98 meters instead of 100. So they cannot just wait for the hydro plants, the mini hydros to go online to finish their 2 meters. They can't. They have to scrap the whole 98 meters. So that's a lot of waste. So even though you get green energy, you're creating a lot of waste when the energy is not reliable. So
Right.
what's more important than than your emissions is actually your efficiency in using your raw materials uh, to produce good products, quality products. Because if they're not high quality, they're going to go to waste. That's terrible for the environment. So therefore, during that time, because I realized that mini hydros are not reliable, I was looking at other alternatives, and I looked at so many solutions. They all require either storage or batteries, which would be nice if we have reliable ones, but we didn't. And then we stumbled upon nuclear. But it's nuclear has a political baggage associated
Mhm.
with it.
Mhm.
When people talk about nuclear power, nobody talks about how much energy it can produce, how advanced our economies could be, how much advanced jobs, upskilling that we can develop, that we can gain from having a nuclear industry. Nobody talks about we can have reliable power, we can have we can have good infrastructure, we can invite foreign investment to build large factories in Malaysia. If you have nuclear power, people already recognize nuclear power's benefits.
Mhm.
We don't have to sell nuclear power's benefits. When people to hear nuclear, all they care about is safety.
Right. Right.
And at the time, I recognized that nuclear has this baggage. Either nuclear safety, we're all afraid of Chernobyl, and at the time it wasn't Fukushima didn't happen yet. It was all every opposition to nuclear was because of Chernobyl or because of radioactive waste. So okay, I thought, okay, this is beyond my reach. Whatever I can learn from the web, this is not good enough. So I decided to do a master's degree. And when I was exploring master's degrees, I was I found this degree in UK, which was called Technology Education Consortium. And what it does is it's a master's program, but it lets the student participate and understand the whole nuclear sector,
Okay.
from nuclear fuel cycle all the way from mining, how you how you refine the fuel into yellow cake, and then you enrich it, goes to the reactor. What and then what's after the reactor? It becomes waste. How do you manage the waste? You glassify, you vitrify it, and eventually you discuss the issues of storage. Why is this storage better than the other one? Why is this more expensive than this one? So it goes through the whole fuel cycle. It talks about nuclear economics, nuclear safety, nuclear physics, and also nuclear thermal hydraulics. So when I took that course, I felt a complete um, fulfillment of myself, that I feel that this is where I want to be. This is my sector. This is where I want to serve the rest of my life. So at the time, Malaysia was also discussing the potential of developing nuclear, of importing nuclear technology into Malaysia. So I went after my master's degree, because I was sponsored by this program called British Chevening. It didn't. This program, part of its contract is, after you finish your masters, you have to go back to the country where you are from, so that you don't compete with other British graduates for those jobs in the sector. So that's fine. So I went back to Malaysia. I returned to the utility company where I started, and we set up. Well, I joined a new setup in the company, because the company was already exploring nuclear energy. So I joined this new division. It's not a division; it's a unit, more of a unit. And we prepared papers for our parliament to consider nuclear power. And while we were doing this, we were already engaging with the public. We were already talking about technologies we want to import, how it's going to affect our economy. And suddenly, Fukushima happened. And when Fukushima happened, well, basically, we fed all the instructions. We understood what was going on in Fukushima, what went wrong. The reactors were different design. There's a boiling water reactor design, and they had fuel at a very vulnerable place, and so on. And so the rest of our days in that unit was just public management, public communication
Could
management, because nobody.
could a Fukushima, like, could a tsunami ever hit Malaysia?
Not in that scale. There could be tsunamis in Malaysia. There was a tsunami in Malaysia that was it affected Bangladesh. Really, really, it was a disaster there, and the impacts were felt all the way to Malaysia, but it was not that bad. And but the point is, we're not going to build nuclear reactors near tsunami sites anyway. So the tsunami didn't flood the whole of Malaysia, just one small part. We're not going to build reactors there. And secondly, even the Fukushima plant, it survived the tsunami.
When did
It just
did you start to assess the suitability of Malaysia as having a reactor, like in terms of the
It's ideal. This is the thing.
yeah?
Malaysia is ideal for nuclear reactors because it's away from volcanic zones, it's away from fault lines, it's protected from tsunami, it's protected by Indonesia, because Malaysia is kind of in the center. Indonesia islands is around Malaysia,
Mhm.
so it's very, very protected. We have good bedrock. We have sources of uranium. With some universities did a scouting study, desktop study, and it's ideal, but the population is not very open, because we haven't really given it serious thought as a populace. And nuclear power is the only power generation technology that requires population buy-in.
Yeah.
If you build oil and gas, if you build coal, if you build biomass, biodiesel, you don't have to get public buy-in before you can build a reactor.
Mhm.
Only the nuclear sector requires this, and that means a lot of investments must go into public communication and public education, and that's why we have this problem. And also because Malaysia is not, we don't take the lead. We're not the kind of populace that takes the lead. We are followers. So
Yeah.
when we follow Australia, we follow Germany, and when these countries show their resistance, we would say to ourselves, "Hey, let's not get ahead of ourselves. If these countries say they don't want to do it, why do we think we're smarter than them, that we could do it better than them?" So it's kind of this
Yeah.
mind game going on in the public populace.
Mhm.
But nevertheless, uh, we, uh, we accept that's a challenge. We just because what people need to understand is that despite the tremendously uh, what's the word for it? Not popular, tremendously spectacular impacts of Chernobyl, of Fukushima. Fukushima only one person, 20,000 people died in the earthquake and tsunami, but only one person died because of the Fukushima nuclear power plant. That's twin disasters, earthquake and tsunami.
Yeah.
But so nuclear has demonstrated that it is the technology that is engineered to be the safest.
Hmm.
But people still have this perception because the nuclear sector, it's also something that the nuclear sector likes to do. They like to share how safe they are, how we can improve the safety, how we can every time you go to a nuclear energy conference, nuclear power conference, every time a company talks about nuclear power, they'll all be talking about how safe it is, or how it makes it things safer. So what the public understand from this is that nuclear is unsafe, and these guys are trying to make it safer. They don't
What I'm
develop the
hearing
perception.
is kind of hearing a subtext is this is leading up to why you chose the design you chose, right?
Yes, 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 yes.
Okay. Okay.
Yes, exactly. So yeah, so after I did my masters, I went back to Malaysia. We tried to start this nuclear program, and then Fukushima happened. And when Fukushima happened, it basically shut down the entire conversation on going nuclear in Malaysia. So I took that opportunity to study further. Is it possible to just eliminate meltdown? Why do meltdowns happen? Is it possible to do it to study it academically in an academic setting? Is it possible to rule out meltdowns completely by design? Is it possible to design a reactor that's meltdown proof? And other people have already done that. Other people are using molten salts. So the fuel is already melted. So how can it melt down? It's already melted. So,
Yeah.
but that's the operation that's the operation condition. It's already meltdown.
Yeah.
So those are the kind of things that interest me. So that drove me to pursue this study, a PhD study at Imperial College with my supervisor at the time, Jeff Hewitt, who was the director of Hanwell in the UK, one of the people who were involved in the nuclear industry since of British nuclear industry since the beginning, until he passed away. And then I got other PhD supervisors who helped me to finish to complete my research. And during the research, we found something based on my discussions with my then professor Jeff Hewitt, that we should be able to completely design reactors that are that eliminate the possibility of meltdown just by using just by using proven fuels. You don't need to go to exotic fuels like molten salts. You can use existing materials, existing knowledge, but just design it differently. And I'm happy that we managed to do that. And at the end of my PhD, we submitted for a patent for an IP for this design. And in February, that was 2 months ago, the patent was published by WIPO. The patent application was published by WIPO. So now we just need to submit the patent to other countries. We've already secured in one country in Europe, and we're just going to submit the same application to other countries to just keep the IP. And we want to develop this system further.
Okay. So targeting places like your own homeland, and anywhere else that you can imagine would want to invest in this, right?
Yeah, so the reactor that we designed is a small modular reactor. So for people who have not heard of that term before, small reactor means that instead of 1,500 megawatts of power that a normal that a typical nuclear power reactor would produce, a small reactor only produces about 300 megawatts. So instead of building 1,500 megawatts, that could take 10 years, that could take 12 years. And in fact, there's been so many delays in existing projects in Finland, in France, in the UK, in the US. Nuclear reactors, nuclear projects, they get delayed, and therefore they experience cost overruns and so on. And so the case for building large reactors, if you can complete it on time, they're very efficient, they're very cost effective. But because there's so many unknowns in a construction project, especially a construction project that lasts nearly a decade, things could change, and your initial estimates might not be accurately reflected in the final project cost. So the small and modular reactor concept, what it does is that instead of the philosophy of it is, instead of building 1,500 megawatts, uh, committing several years for it, committing a decade for it, why not just build a 300 megawatt reactor now, finish it within 3 years, and then once that's running, you use your income. You now, because the reactor is running, you're already selling your electricity to the utility. You're already getting income, and you use that proof of income to finance your second reactor, and then finance your third reactor. And once you build your 5 reactors, you're now equivalent to the large conventional plant, and you might even complete the whole 1,500 megawatts that you desired
That's good.
within a shorter period of building just that one large reactor that needs 10 years before the investors get their money back. And that's the case for small modular reactors. And that's the kind of reactor that we design also at Imperial.
And there, people are don't take as big a risk if they're an investor either. Like it seems to be that there's
That's right.
not as much
That's right. That's
funding.
right, because many infrastructure projects, especially in the West, are privately funded. And
Mm,
because they are privately funded, these things matter. The risk, the financial risk, the time before you get your returns, and so on.
right. Okay.
Right.
Okay. Very good. And so yeah. So I know that you mentioned some of these more exotic like molten salt reactors, and I take it that you didn't take that route. You yeah. I'd like to hear. Let's hear. First of all, what do you call your reactor?
Right. So the reactor we design. Let's start with why we designed it, how we designed it, and why it became a design. It's okay. So,
Know why you're not jumping
uh,
the name because you haven't come up with a name that's catchy yet. You have a name that
yeah,
is
it's
describes
an engineering
exactly
name.
what it
It's a code name. Yes, exactly. And that's how we work in science. The name is the name is what it is. It's a description. It's not.
is.
It's not really a name.
Yeah, yeah.
We played around with names before, but we haven't narrowed it down yet. So what? So the thing is, the nuclear industry traditionally, and even nuclear industry, even nuclear people who are listening to your podcast now, people who are already deep in this sector, they would still hold on to this. They would say, let's improve thermal efficiency of the plant. Let's improve the efficiency of the plant. Every new plant that we build, let's build it with higher efficiencies, which makes sense. Which makes sense because all sectors, all energy sectors, not just energy sectors, production sectors, and everything else, you care about improving your thermal efficiency, your energy efficiency, only if your fuel is expensive. So it makes sense if you're in oil and gas industry. When you develop your turbines, you want your turbines to be the most efficient as possible because your fuel is expensive. The more efficient your turbines are, you're already paying for this amount of fuel. The more output you get, the more money you get. So that trickles down to every other sector like coal and even nuclear. So our nuclear reactors in the past, their efficiency was 29, 28, and then 31, 32. And our most modern reactors right now, like the European pressurized reactor, I think its efficiency is between 35 to 38%. So they've really, really improved the thermal efficiency of the plants. However, to achieve high thermal efficiencies, they need to go to higher and higher pressures. So the system pressure in the pressure vessel, in the safety systems, the pressurizers, the piping, the heat exchangers, they all have to be able to maintain this higher pressure that they have designed their reactors to operate at, so that they can produce high thermal efficiency. But building these equipments rated at these pressures, they are expensive, and the safety equipments, the safety systems, that if you're trying to inject fluids into a pipe that is rated at 150 bars, that means your injection system has to be higher than 150 bars. Otherwise, you won't be able to push any fluids in.
Mhm.
So your safety equipments now have to be rated at higher than your operating pressure. So all these, they lead to costs. They lead to complexity, and therefore they lead to higher costs. That's why reactors have become so expensive, because you don't just need one of these pumps, that high pressure injection system. You don't need just one. You need at least three. You want one that's operating. You want a spare one, and you have a third one, so that if one goes under maintenance, you have at least two that you can count on, so that if one fails during operation, you still have one backup that can still shut down your reactor. So you want at least three. But if they're all powered by electricity, what if something happens to your grid and you can no longer power these three high pressure injection systems? So you need a fourth one that's powered by diesel,
Mhm.
or an alternative that's not electricity. And so the minimum, you need three of the same kind, and one, so three redundant
Yeah,
and one diverse. So,
sure.
but plants like modern plants, they have another one. They have battery. So you have two redundants and three redundants and two diverse injection systems.
Hmm.
I just noticed myself on camera just now. I was holding this. This is a Canadian iron ring, so you might appreciate this, or people from Canada might appreciate this. So I am a Canadian engineer. I graduated as an engineer in Canada, and this is my iron ring to prove it.
Okay, nice.
It's only given out in Canada. If you're not aware, only Canadian graduates get this iron ring. It
Oh,
proves that they're engineer, and there's a story behind it, and it's a very interesting story. I think
yeah, I'd be
you
glad.
might have this interesting discussion with other Canadian engineers. Why Canadian engineers have this ring? It's actually related to safety, and I think it kind of drove me to what I'm doing today. So to summarize, this ring is given to all Canadian engineers. It's worn on your working finger, so that when you do work, sometimes it hits the table or hits whatever you're working on, and it makes this sound. That sound reminds you to not screw up, not take things for granted. Because when you make that sound, hey, maybe I've been cutting corners a bit. I have to do better, because this ring makes while I'm working tells me to do a good job to ensure safety.
Yeah.
So it's a really nice story behind it, and the story is a bit deeper than that. That was just the surface.
And it just, you said it's
Yeah,
an iron ring. Is that what you said? Made of iron?
iron. Yes, yeah,
Oh,
it's made of iron. It supposedly came from this bridge that collapsed in Canada. I think it was 1917, 1920,
okay.
and the first rings were made from the steel of that collapsed bridge. So, but
Yeah.
eventually,
If I was an engineer, I might know about it. That's the first time I heard of that. Okay,
right.
shows you
So
my
yeah,
my background.
right.
Yeah.
So yeah, so there's a whole cult behind this ring, because to get this ring, you have to have someone who's already has an iron ring to put it on your finger. There's a
Oh,
ceremony behind it.
yeah.
It's really nice. I really liked it, and I think because of this, I turned into the person who I am, who really cares about improving safety. It's because people are driven by economics, right? Make things more efficient. Make things more efficient. I say my philosophy is a bit different. Like, make it safe, but not make it too safe. Just make it safe enough that you have a safety margin to everything that you do. Don't sacrifice your safety margin. So, and that goes behind the that's one of the driving principles of the reactor that we design anyway. So, following going back to that, so instead of going high pressures, we kind of took a different approach. We tried to study, what if we go the other way? What if we just go to low pressure systems instead of high pressure systems? Because we recognize what are the problems associated with high pressure systems. What the study was, how much do we sacrifice if we go to low pressure systems? So when I said before, if you're running a reactor at 150 bars, 50 bars, your efficiency is going to be 30% to 35%, and the higher the pressure goes, your efficiency only get your it's already saturated. The curve has already saturated. So if you're at 50 bars, your efficiency might be 33%. If you're at 150 bars, your efficiency might be 35%. You only gain 2%, but your pressure, your complexity in your reactor, the quality of all the materials has improved in several magnitudes in scale.
Okay,
So,
good.
but what
Just
if,
just a quick aside. What is
right?
the typical pressure or bars? How many bars in a conventional pressurized
Yeah,
water reactor?
Sure. In a pressurized water reactor, the conventional pressure is about 150 bars.
Oh, okay, that's why you
One
showed me
flat.
that number. Okay,
Yes, yes.
okay,
Boiling water reactors, it's about 50 bars.
okay. Interesting.
So
Quite
so yeah,
complex.
so that right. So that's why those numbers are easy. Just the top of my head because I compare them with the typical conventional established designs, and so. But when we did the study, when we went the other way, instead of 50 bars, let's go the other way. So we found out that at about 5 bars, 5 bars operating pressure, the efficiency is like 18%. So 18% is remarkably worse than 33% when you look at the numbers. But when you do the comparison, that's only half the efficiency of this huge, complex, conventional large reactors because they're at 150 bars. All your equipment have to be rated at 150 bars and above. But at 5 bars, that's your commercial scale building. That's the water your water faucets in your home. That's about 3 bars. That's a reduction in complexity, in a reduction in your engineering barrier to the barrier of entry to this technology. It's just 5 bars is very very accessible, and the efficiency is not that bad. Of course, it's bad. It's like only 18%, but that's only half.
Just an aside on the word efficiency and percentages.
Mm-hmm.
Is
Mm.
there some formula you use to determine efficiency?
There's no actual formula, but we did develop a simple formula. But the way you actually analyze it is you have to do this TS diagram. You have to do a Rankine cycle analysis. Uh, it's something that a bachelor's degree student can do in 30 minutes to 1 hour. They'll be able to do this analysis, and you have to do what you do is you do it at 30, you do it at 50 bars, then you do another one at 25 bars, you do another one at 20 bars. You do this analysis,
Okay.
full analysis at this, and then you just draw a line that connects all the dots that you've done at 50 bars, 45, 40, 35, 30, and then you just draw a line that connects all those points. And from that line, you can actually get an equation for it. So, yeah, so that's what we did as well. But we didn't use the equation. We just did the analysis, Rankine cycle analysis at each of the pressure points. And the thing is, what's important to know at 18% thermal efficiency compared to the 35% thermal efficiency, 35% and 18%, that's about half of it. What is half of thermal efficiency? It just means that you're consuming twice the amount of fuel.
Hmm.
Uranium fuel is very, very cheap. Uranium fuel is it's not like oil at $100 per barrel. It's it's like $50 per pound.
Hmm.
That's how cheap it is. And per pound, uranium is a very very energy dense atom.
Yeah, a pound.
When you talk about pounds, that's huge amount of energy that you can extract from that. And if you're doubling your raw fuel, that's very very cheap. So what? That's basically what thermal efficiency is.
Hmm.
That and when the industry has been pursuing higher and higher pressures to improve efficiency, all they're trying to do is instead of using 100 grams of uranium, they just want to use 99 grams of uranium. But the price is like, instead of 55 let's say $20, instead of $20 you want to reduce it to $19.8. So it doesn't really, of course those numbers are upscale. I mean,
Yeah.
but it's just an example of the scale of savings that you get from just trying to improve your efficiency. But the benefits of going to low pressures, yes, you would increase your operation cost, but you amplify your safety margin, because at low pressures, you don't need such complex equipments. Your skill, the skill that people have to acquire before designing, building, and operating this power plant, it's not very high. Many these equipments can be built in high quality in factories, with high qualities in factories, and also because they are simple, eventually that translates to the price. It's cheap to build. So what it is instead of reducing your operating costs, nobody would argue that operating costs of nuclear power plants are expensive. They're not. But the capital cost, everybody knows, it's very, very expensive to build a reactor, but cheap to run. So what we're doing is just we're changing this capital cost requirement, which is reducing that by a magnitude, but the operating cost increases just a little bit, because and that's how that's why our reactor is expected to be significantly cheaper, much cheaper than whatever else that exists in the market if we
Good.
get to build it.
Okay.
So the reactor name that we've assigned to it right now is Low Pressure Water Reactor. So because it's a low pressure,
Yeah.
and it's a water reactor because we have a lot of experience with water reactors. We've been building reactors, water reactors, for 60 to 70 years,
Mhm.
and because of that, we have a lot of knowledge with water reactors. We know the corrosion patterns. We know how water interacts with zirconium at this temperature, at this pressure, what is going to happen. And even after 60 to 70 years, sometimes we still find new mechanisms of corrosion. So that's even after 70 years. So if we go for molten salts, yes, it might work in the ideal conditions, but imagine not having that 70 years of experience
Mhm.
as you have with water reactors.
Okay. Yeah.
What are the mechanisms that you haven't discovered yet?
Yeah.
So that's why we decided, let's keep it simple. Let's see how far we can push water reactor technology, and how far we can extend the water reactor technologies based on our knowledge. Equipments are already off the shelf. We don't need to design new equipments because we're already using stuff that are already used in other power plants, but
Okay.
we're just using at low pressures.
And you have an existing supply chain, like
Yes, exactly. The supply chain exists and it's available and it's ready to supply.
now, if you needed, like for instance, the solid fuel, there's companies that create these pellets for. Is that the same notion that you would use?
Yes. Well, basically, in our reactor design, we try to minimize the actual reactor design, the actual fuel and assembly design. We're just going to buy off-the-shelf fuels. The reactor right now is based on the EPR fuel, the fuels that are already supplying the new EDF, European pressurized reactors. And of course, we can even we want to use that because that's readily available. But any manufacturer of reactor fuel, other reactor fuels, they can also, technology wise, they can also manufacture this fuel easily. But whether they are licensed to do that, we don't know. But our right now we're just keeping it simple. We're just assuming, hey, we'll just use the EPR fuels. We just buy it from them.
I'm sure that viewers would be anxious to see your models and your design. Do you have? Do you want to maybe pull out? Maybe share your screen and show us some things.
Sure, I have a kind of a simple model, a sketch of a conceptual how it's going to look like. Of course, it's not perfect. We haven't got proper designers for this yet.
Okay.
Um, so, how the reactor works? I think I might need to describe how the reactor works first. So, I think I'll share um, something else. I'll
Okay.
share this one.
No problem.
Oh, share screen.
Yeah, and you choose full screen. Yeah.
Yep, I'll choose full screen, but it's not letting me choose this screen. Okay, so
Okay.
we
Good.
can see that, right?
Yes.
So let's start with the typical boiling water reactor design. Just a simple schematic. It's more complex than this, but when you try eliminate most of the unnecessary components for demonstration, this is all it boils down to. So you have a reactor core here, and water is pumped from the pump, coolant pump, all the way into the reactor core. Some boiling water reactors, they may not have coolant pumps. They might have other internal circulation systems, but the function is still the same. The idea um, is to make fluid flow into the bottom of the reactor core, where the reactor core starts to heat up the water, the working fluid, and it converts it to steam. And the steam is separated from the moisture separator, where you remove wet steam, you remove moisture from the steam, and the dry steam, only the dry steam, goes to turbine generators. The turbine generator will generate, as they spin, they will generate electricity like a dynamo on your bicycle. So you start generating electricity, and the steam that comes out of the turbine generator goes to the condenser. So the condenser, actually, what it does is it creates a vacuum. So this is high pressure at 150 bars or 50 bars in some boiling water reactors, and is the pressure is about 0.04 bars. So that's a huge difference in pressure. That huge difference in pressure drives this turbine. So after the steam goes out of the turbine, it's condensed. So think of a condenser as like think of a network of pipes that goes on the ground level and then dips into a lake and then comes back out. So that's basically what a condenser is.
Oh,
Uh,
is there a heat sink? Is that like you say?
yeah, if you imagine a heat sink, so a condenser is connected to a heat sink,
Right. Okay.
and this heat sink is where you extract heat out. And once the steam loses its internal energy, it will become water again. So that's a condenser. So um, for the man on the street, just imagine a network of hot pipes, a network of pipes containing hot water, and these pipes go into a lake and come back out on the other side of the lake. So that it's hot on one side of the lake, and it's a lake temperature on the other side of the lake, because the heat is now absorbed by the lake, and your pipes are already cooled on the other side. And that cool pipe now goes to the coolant pump, and gets pumped back into the reactor core. So the thing with this is that to protect this pump, you need a lot of systems to ensure that pumps are always running. At least one pump. I'm just drawing one pump. There could be multiple. Usually there are at least three coolant pumps, and you need several accessory systems to ensure that the pumps always run. Because if the pump fails to run, then cooling cold water will no longer be supplied to the reactor core. So the reactor core will start heating up above its melting temperature, above the fuel assembly, the fuel pin. It's stainless steel on the outside. When its temperature reaches above its glass transition temperature, it will start to melt. And once your rods start to melt, it will swell. And once it swells, it will block further flow, and eventually your flow will stop. And that's the initiating one of the initiating events to a meltdown. So you want to ensure none of your fuel rods ever swell, and to ensure that, you have to ensure the water inside the cooling fluid inside your system never stops, never becomes stagnant. You always want them to go through this cycle. So heat is absorbed and then removed. Heat is absorbed and removed. You want to retain that cycle throughout the lifespan of your reactor. And this is why reactors are very, very expensive, because one is you need pipes that are rated at these pressures. Then you need equipments that ensure the pumps will continue causing fluid to flow in your reactor cycle. But in our reactor design that we developed, so we have a reactor core. Now it's further away vertically from the moisture separator, and we move the turbine generators, condensers on the same level. And what you have now, so this reactor core now sits 100 meters below ground, and fluid that comes out of the condenser, because this is all liquid. After the condenser, it's all liquid. This is all liquid that goes down this pool. Just ignore this water pool for the moment. So it goes all the way down water and enters the reactor core inlet. But once it enters the reactor core inlet, it starts to be heated up. It gets heated up to just below saturation level. So what that means is, if this is below ground, we design it to be about 100 meters below ground. That's about 12 bars. So it exits this. So at 100 at 12 bars, the boiling temperature is no longer 100 degrees. It's about 120 something degrees. So we boil it to about 115 degrees Celsius. So it's still water. It's still water completely, because at high pressure, you're not boiling at 100 degrees, even though this is 115 degrees.
Yeah.
But it starts to become steam through the process of flashing, because the pressure here is no longer 12 bars. The 12 bars is here. At about 7 bars or 8 bars, the water that was at 115 degrees starts to become bubbles and eventually become steam. And this steam then goes to the moisture separator, and the steam is isolated. Only the steam goes to turbine generator, and this is at 5 bars. So this 5 bars generates power to the grid at about 18% thermal efficiency. Then it's condensed back. But if you look at this is water, completely
Mhm.
water, flooded with water. This line is just steam. So water is high density. It's about 1,000 times more than steam. So you have, imagine a heavy piece of metal on this side, and well, that's not a good analogy.
Oh,
Just imagine water and steam. So that's going to be a force that pushes through the reactor because of this difference in density from high density water column to a low density vapor column. And this difference in density is going to cause this flow. So this flow is going to be naturally sustaining without any use of pumps. It's a naturally driven circulation, hot at the bottom, cold at the top, and you have this natural circulation system. And because of that, you no longer need pumps, and you eliminate loss of coolant accident, because you now dump your reactor inside a pool as well, and the reactor will never run out of water.
and
And it's
so
also
that
single phase.
natural, you called it natural. How is it natural?
Yes. Natural circulation is because one side is high density and one side is low density. So you have this force, this driving force that
Right.
pushes water through there,
You
and
called it the
you don't
siphon.
need to pump the water. You don't need
It's
to pump the water.
it's the siphon effect, right? We talked about that.
Yeah, exactly. It's the siphon effect. So
Okay.
this siphon effect is what causes this natural circulation in this system. Exactly.
Okay. Good.
Yeah, and also it's also because we're not boiling the water inside the core like boiling water reactors, where the steam is actually produced at about this point. Therefore, all the core is dunked underwater, meaning the neutronics are all based on single phase. I mean, it's all liquid. Like I said before, the density of the water molecules is about 1,000 times higher than vapor. That means the molecules of water are much closer together, and you have a very stable moderation effect inside the reactor. Instead
Okay.
of,
Yeah.
if it's water becomes steam, then suddenly you lose your moderation effect, and then it starts to, the reaction slows down, and then it becomes water again. So you have this oscillation condition inside the reactor, where your neutronics much dependent on the feedback of your cooling system becoming water, then steam, then water, then steam, then water, then steam. So that's
Yeah.
not good for the reactor.
Depending on the level of knowledge that the listener has, they
Right,
they would have assumed you meant that the only moderator here is the water, right?
right. Yes.
A lot of
So
reactors have other moderators, but
yeah, correct. Like Chernobyl, they use graphite as a moderator, but in most water reactors, I'm well, um, one could argue that Chernobyl was also a water reactor. It is not. It's more. It's a graphite moderated reactor, but it uses water as a cooling system. In Chernobyl, water is used in the core, but as a coolant only. The moderator is graphite. In water reactors, like pressurized water reactors, boiling water reactors, and also this reactor, the moderator and the coolant is water. So water is used for dual purpose.
okay, yeah.
So not only does it extract heat from the core, it also provides feedback to neutron reactions in with uranium inside the core. So if you don't have water, you won't have much reaction in the, well, it's called the negative void feedback coefficient. As your water becomes steam, your reaction suddenly drops. But then, because your reaction drops, it becomes heat is produced less. Then it becomes so when heat is produced less, the steam becomes water again, and you have this terrible feedback
Is
mechanism.
there
And
is there some function about the dry steam that's better than wet steam for going to the turbine?
sure, the reason why dry steam is better for the turbine is because there are water molecules in the steam. In wet steam, where not all the vapor, because some water droplets are carried along with vapor. So these water droplets, when they hit the turbine blades, they could eventually damage the turbine blades. Over time, you'd have vibration issues because the blades are no longer perfectly balanced with each other, and therefore you want to minimize water droplets that reach the turbines. Therefore, that's why you want dry steam as possible that goes to the turbine. In conventional reactors, not just reactors, in conventional coal plants, you have your high pressure turbine section, you have your medium pressure turbine section, and you have your low pressure turbine section. That entire cascade is just called a turbine, but the high pressure turbine section, it's very, very vulnerable to these water droplets because they are operating at a different level of efficiency,
So,
and therefore you want to minimize.
am I making an assumption that most reactors want to use dry steam?
Yes, well, all reactors want to use dry steam.
Oh, okay. And
All
so
reactors.
that extra distance somehow enables
No, no, no.
more,
This distance doesn't tell anything. It's just a connection. Um,
it's just for
the,
the
the
effect.
it's just for this diagram. There is no it's not shown to mean anything other than it's connected to each other.
Oh, okay. So but your purpose for the natural aspect of it is that's why you dig down deep to get that flow of
Oh, okay. This vertical column, yes.
yeah,
Do you see my mouse cursor?
yeah, I do.
Okay. So, okay, because it could lead to confusion if you can't see it. So this distance creates, first of all, it governs the natural circulation, how much flow is created. In this case, it's about 15 tons per second that we can create just by natural circulation by putting 100-meter vertical distance between this and this. This and this, they're all together on the same height actually, but I drew it this way to just optimize the space. Moisture separator, turbine generator, and condenser, they actually exist on the same level. So putting a reactor 100 meters away, 100 meters below this line creates a driving a mass flow rate of about 15 tons of water per second in the
That's
core.
huge. Wow.
In a conventional pumped system, like the main reactors, like the AP1000 and other pressurized water reactors, that's with the pump.
Yeah.
They produce about 20 tons of flow of water per second, but we achieved 15 tons. So that's three quarters
Without a
of
pump.
the pumping power without a pump.
Wow.
Exactly.
Amazing.
Just by natural circulation. That means we could completely remove coolant pump from this. Of course, we're not pumping 20 tons per second. We cannot. I mean, there are ways to achieve that, but it's not optimum for our purposes. But 15 tons, that three quarters of in comparison with the large conventional reactors, achievable mass flow rate, I think that's quite impressive for a natural
Um,
circulation system.
so the heat from the fission is partly responsible for that driving force.
Yes, definitely.
Oh,
Because the heat from the fission converts the water to steam. And this steam, because it's lower density, meaning, think about it this way. this is not a good example. If you have a glass full of water and you have a glass full of steam, and you put both of them on a scale, the glass with water is going to uh, it's going to be heavier than the glass full of steam,
Okay.
and that kind of force is what creates this driving force inside the reactor core.
Okay. That's
It's
really
because water is
fascinating.
heavier
And
than vapor. It's not
so,
really heavy. Sorry.
has nobody done what your design does? Like,
Yeah. So
it seems so rational.
well, it took time to develop a natural circulation system, because we understand natural circulation from some basics. We know that heated fluids tend to go up. Like if you boil water in a kettle, you would see steam coming out from the kettle, but and the direction is up. It doesn't The steam doesn't go down, it doesn't go sideways, it goes up. So we
Mm-hmm.
know that hot fluids tend to go up.
Mm-hmm.
And if we use air conditioning units in your homes or your offices, you know that the air conditioning units are mounted at the roof, not a roof, at the ceiling. It's because cold fluids tend to go down. You don't mount your air conditioning system on the ground level or on the floor. You put it on the ceilings because cold fluids tend to go down. And to connect these two phenomena into a system like this, it's in hindsight it's so obvious, but it's the I guess it took. I guess it takes stepping out of the box to be able to to look at this in that way. And I have to say that I'm not the first to develop natural circulation. For Westinghouse developed the AP 1000 nuclear reactor with passive safety. That means they have natural circulation with a siphon effect, but during accident conditions, meaning their safety systems are operating with natural circulation, but no other reactors, water reactors, operate on natural circulation. There are new reactors that run on molten salts, or that use a natural circulation phenomena as well, and
Yeah.
also the GE Hitachi boiling water reactor. They also use natural circulation in their operation, but not like this. They do it in a different way, in a boiling water reactor style. Um, but no, but they're not they're not doing it the same way that we achieve about 15 tons per second of mass flow rate of
Okay.
water into the core. It's So
And
we completely depend on natural circulation for the operation of the plant.
there's like, I think we talked a bit about this when we weren't recording, about the how you determine the depth, 100 meters.
Right. Right. So that's interesting. If you look at this, just imagine if you have steam
Mm-hmm.
on this line and water on this line. So
Yeah.
you can imagine that the water is going to push through and go out to the other channel, because this high density and low density. But if you're low enough, if this is not that deep, if this is just 10 meters below ground, your steam volume, steam height, the height of your riser is now very, very short, and the water line, the water, this downcomer distance is very, very short. So you kind of still have natural circulation, but you won't get but it's very, very little. That your mass flow rate is very, very small, because you still have natural circulation, but you don't have enough steam. Or you might have hot water and cold water. There's still a difference of density, but it's not 1,000 to 1 difference. It's just hot water, the dense uh, it's just hot water is just less dense than cold water, but you still have some mass flow rate, but it's not very large. You won't be able to run a reactor system on that. But if we go deeper, like 200 meters, maybe 1 kilometer, the thing is, steam is produced about that point.
Mm-hmm.
So the further below ground you move these 2 points, your steam is still produced at this point. Your steam is still produced at this point, even if you move this reactor down below. It's because that's where the pressure is.
Mm-hmm.
That's where the pressure, the saturation point is. where your pressure is low enough that that your reactor that you heated up to below saturation level now becomes steam. So when so your steam line is still up to there, and your this point is still water, and all you're doing it if you're doing it 1 kilometer instead of let's assume this is produced at 70 meters. This is 100 meters. Let's say this is 70 meters. So you have this 30 meters. So when you move this 1 kilometer below, you're going to have about 970 meters of water, and then it becomes steam. And this is you're going to have 1 kilometers of water. So this cancels out. This point, this part cancels out this part. What matters is your how far is your steam distance and how far is your cold water distance. That's the density difference.
Mhm.
That's the density driven natural circulation. Is the difference in density. If you have 100 kilometers, you're just going to cancel out with this 100 that 900 sorry 100 99.7 kilometers of water before it becomes steam. So
Yeah.
you just so
Okay.
that's basically how why we chose 100 meters as our depth. You can go further, but you have improved safety because now your pool of water is going to be lengthened, but it's just not. You can do it if you have the luxury of doing that. Where we don't think there is a case to do that.
Now we know that these kinds of diagrams are always simplified. So
Correct.
now, if we had to talk about this concept of channels,
Hmm.
where are these channels, and would that diagram get a lot more complex if you tried to include them all?
I can try to show you something else. It's a rough idea, still simplified, still very, very simplified.
Mhm.
So this is actually how our reactor core eh, is going to look like. Well, roughly. So you have this fuel assemblies inside. So you see one, two, three, four, five, six. So these are the fuel assemblies. This entire orange thing is called the core.
Mhm.
So water flows from when I showed the simple schematic, just a 2D schematic with just lines. So the downcomer, where I described the high density water, it's actually on the outside of this cylinder of this shaft,
Yeah.
and this shaft is hollow in the middle. So this water goes through the reactor where it gets heated up, and it goes up through the hollow center of this cylinder of this shaft. So water goes from the outside, from all around it, from there, from the front, goes in between these channels, and this is water, and it becomes steam up
Okay.
there.
So the orange part
Really.
has quite a few channels.
Yeah, so these are fuel assemblies. Inside fuel assemblies, there are fuel rods, and so water flows in between those fuel rods. So that's a channel. So you would say, oops. So you would say a channel like let's see if I can do this.
Are your fuel rods
I can't.
specifically designed for your reactor, or are these things you can get?
No, these ones we buy off the shelf.
Oh, wow. Really? Okay.
Yes, we buy, but we have different arrangement.
Yeah.
So the way we do it is we buy these fuel assemblies off the shelf, and but we design it in a different way. We arrange it in a different way to optimize flow and optimize energy extraction by the fluid.
Okay. Interesting.
Sure, thanks. And yeah, so just to zoom out, if we do 100 meters of this reactor, this is how it kind of looks like. So this 100 meters below ground, and steam is produced somewhere at that point, and it goes to this moisture separator in the middle, and the steam goes to the turbine generators. So we didn't really model this in cosmetically. We didn't really pay much attention to the turbine generator part. We improve. We want to show that this chamber is where the moisture separator is,
Yeah.
and there's a huge tank here that's filled with boron. So the concentration is about 1,500 parts per million of boron inside this tank. So when we want to do refueling, what we do is we open these valves. The borated water will now flood these chambers up to about that level. So we can remove our fuel rods, store it in the fuel pond, and insert new fuel inside the core, and there will be no reactions because the entire thing is flooded. we can just simply move these components around, and everything's inside water. Everything's inside borated water,
So
and
how often do you do that?
typically, one fuel assembly will remain in the reactor for about 5 years,
Oh, okay.
but we refuel it every 18 months. So what it does is every 18 months we'll remove a third of the core, a third of the fuel assemblies in the core. We'll remove it and insert a third of the fresh fuel assemblies into the core. So, but
Does
one fuel assembly will remain for 5 years.
So the fission gets like they become used, I suppose, and you have
Yes.
to replace them. Okay.
Yes, because fresh fuel, they'll have more reaction.
Yeah.
And so if you put fresh, 100% fresh new fuel inside your core, um, at the start, they'll have a lot of reaction, but nearing your 4.5 years, that's when your reaction suddenly you won't produce as much reaction. So you want to kind of so you every time you refuel the fresh fuel, every time you insert new fresh fuel, your reactivity is high. But at the end of your fuel, at the end of your 4.5 years, when the fuel has already been 4.5 years in the core, the reactivity will be much lower. And then when you refuel, it starts to become high again. So there is kind of a oscillation in reactivity if you run it for 40 years. So we don't want that. That's not nice. So what we do is we just change a third of it. So that kind of flattens that. So when you just only change a third, so you have a third of fresh fuel, you remove the third. Oldest third in the core, and you refresh that with new fuel, and every 18 months you do it again, so that kind of flattens that reactivity difference between fresh fuel and old fuel.
While you were talking, I was thinking about the idea of ramping up the power. Is that a
Mm-hmm.
possibility with your reactor?
Sure. Well, ramping up power, that's
Or down?
normally for nuclear reactors, we don't load follow. What that means is that as power demands in the grid increase or decrease, reactors do not follow that load. They just generate at a constant rate. But what can be done? You don't really load follow. But if you have let's say 10 1000 megawatts 1000 megawatt reactors on the grid, you can actually let's say you have 10 1000 megawatt reactors on the grid, but you run it at 900 megawatts each of them,
Right.
and you suddenly need another 1000 megawatts of energy. So what you do is each of these reactors, you just run it at 100%. Then you have your extra 1000 megawatts.
Okay.
And when you don't need it, you run at 900 megawatts each reactor. So you have a 10% margin where you can ramp up
Yeah.
to meet your demand.
So
So you do it as a fleet.
you always run below its capacity.
Right. It depends on the utility how they want to manage this, because it's nuclear reactors are really cheap. You kind of want them to run all the time,
Yeah.
but because they don't load follow very well, so you do it as a fleet. But if you have other technologies like quick firing gas plants, then you might use that to load follow. It depends on the economics of the utility grid in question,
Yeah,
how they want to
I
do it.
know that there's discussion of having something like what these solar farms have, the molten salt as a source of heat only,
Right.
and
Yes. Yes.
they
Yes.
can become load following in a sense, right?
And nuclear reactors, some nuclear reactors can do that. I mean, they're not used like that now, but some many nuclear reactors, if they generate 1000 megawatts of electricity, right, but the demand is only 900 megawatts of electricity, instead of wasting that 100 megawatts, why don't you use that for district heating? Why don't you use that to generate hydrogen
Uh-huh.
from electrolysis and so on? You can use that
Divert that extra energy.
exactly. So instead of load follow, what you do is when the load is not enough, you just use that extra energy for something else, something more useful, like
Mhm.
generating hydrogen.
Yeah, yeah. Interesting. Very interesting. Yeah.
Yeah.
Wow. Okay. And so, how about what kind of steps do you need to take to make a physical reactor, like to get to that stage?
Oh, that's a lot. Well, for us, we only have a general concept where we've studied desktop study of how the reactor is going to operate, what are the safety case, like how far away it is from departure from nuclear boiling, for example. But we still need to do a lot of design, component level design. For example, our moisture separator, we can't use the ones off the shelf now. We need to design the most efficient moisture separator because our temperatures are not high enough. We're only at 120 degrees C compared to like boiling water reactors. They boil around 300 degrees Celsius, so they have a much drier steam that they can use to go to the turbine. But then again, we don't really need high quality dry steam in our case because we in like I said before, you have the low pressure, high pressure part in the turbine, you have the medium pressure part in the turbine, the low pressure part of the turbine. In our reactor, we just want to use the low pressure part. We don't need to use the high pressure part, so we can have some wet steam. But still, we want to be sure that we have a very efficient moisture separator because this is a natural circulation. We cannot produce flow. So any parasitic any friction in flow
Yeah.
is detrimental to us. So we want to have the most efficient equipment as possible. Although there are some in the market, we want to do more research on how to design a better one, or if it's possible to design a better one. And all the other systems, like it's not shown in this diagram, like chemical processing plant, it's also inside this circuit, and we also want to optimize that. And also we want to improve we want to redesign the shutdown mechanism of this reactor, because normal conventional reactors, the reactor core is on ground level. They can have the control rod mechanism right above the core. There is so you have your control mechanism package where you drop the control rods. It just sits right above the reactor core.
Yeah.
But because we are now, the reactor core is like 100 meters below ground,
Mhm.
do we want to move the control package together with the core 100 meters below ground? We have to decide that, or we want to keep up on the ground level so that we can maintain it, and so on. But then, how are they going to insert control rods 100 meters away? So we're going to study. We're going to have to develop other systems. Like maybe we'll inject control rods from the bottom with springs instead of using gravity, where your shutdown rods go down by gravity. Maybe we'll use springs to inject it from somewhere, or maybe we'll license the Toshiba design, because the Toshiba 4S reactor design, they have a shield that reflects neutrons back into the core. Maybe we'll figure out something along. So what they do is, if they want to shut down the reactor, they just drop the shield out. Neutrons will leak away from the core, and the fusion reaction will shut down because they won't have enough neutrons. So we might explore that kind of solution. So we need to raise funds to develop these kinds of some more complex component level engineering
So
to
the
finish
funding
out.
raising, like, okay, I guess there's different stages of funding, right? And
Correct. Yeah.
so you're in the kind of the beginning stage.
Yeah, we're still in R&D stage. We need to raise funds to develop these. So before we can have our final, let's say, plant blueprint, we still need a lot of work to do. We still need to develop some engineering level designs. This might lead to new patents or IPs. It may not, but we need to put. We have some ideas how to control reactor. We already have an idea how to shut down the reactor, but we want to see if there are anything better than what we've come up with in the
Okay.
past.
Yeah.
And we have some ideas, but we need to put numbers onto them. Like we have, oh, why don't we use this? Why don't we? Yeah, we can, but we
Mhm.
need to quantify them. We need to ensure, okay, what are the parameters, up to what limit, what's the minimum, what's the maximum. We need to do a proper a research level judge, so that we can have a research level, an informed judgment based on
Well,
established research.
does funding right now, like, is that stopping you from moving forward, or are you
Yes.
okay?
Yes,
So
but it's also because the patent was only recently published. Now we can talk to people. We can share a lot more information now that the design is protected.
mhm.
Before, it was people argue that don't share too much because somebody could just run with the design and build their own. But now that it's protected, nobody can patent the same design. We're now more open to speaking about it, even speaking publicly, even speaking with you,
Yeah.
which we wouldn't be able to do just 2 months ago.
Yes, interesting. Yeah. So, so you're basically the project is on hold then.
Um, well, the research is on hold. The
Yeah.
research is on hold,
Okay. Yeah.
but because we need to get funding, we need to engage with universities because we want to do this research at universities. They have facilities that we require,
Okay.
and they have the software that we require,
Okay.
and all the other stuff. So yeah, so the funding that we are raising is to develop these relevant the technologies relevant to the design that I showed earlier,
Okay.
and
And
so
Sea Energy, I think, is what you called your. Is that
yeah.
where did that name come from?
Right. So the company is called Clean Energy Expeditions.
Oh, okay. Clean Energy.
So the logo is actually C Energy X. If you
Oh,
look at it,
okay. Yeah.
so it's a fancy way of writing it.
Mhm.
So that's Clean Energy Expeditions. And why we chose that name is it's actually um, quite ghetto. I would say it's because the domain name was available. That's why we chose that name.
Of course. Yeah.
Yeah.
Oh, that makes sense. Sure. Even that name, it's not a name for a reactor. It's a name for a company. So who knows what your reactor may one day be called?
Yeah. Well, the thing is, this company that we set up, we're not just going to only have this one design. One drawback of this design, when I said that it consumes twice the amount of fuel,
Yeah.
what that means is it's also going to produce twice the amount of waste.
Mm-hmm.
So eventually, we are going to develop. We're going to, now we think it's too early to do this, but there are already other companies that have already got ahead of this. What they've designed is run reactors on nuclear waste. There are many reactors that run on nuclear waste, like even Bill Gates developed a different kind of reactor that runs on its own waste, but that cannot accept waste from the outside. So we want to develop other reactors that will run on the waste that we produce, so
Right.
that we extract as much energy from
Got
our reactor.
You've got a few people in the race for that.
Right.
Oklo, if I remember right, is
Yes.
designed on that
Yes.
principle. Yeah.
Yes.
And
Yes.
but yeah. So but the regulatory system is not very friendly in the United States. Um,
Right, and it's also our case. That's why we actually identified the challenges Oklo would have faced, which they did face. It was because they were using really exotic materials, exotic techniques that the regulators were not familiar with. The regulators need to be trained to the level of the Oklo engineers before they will become comfortable in their in their design certification approval. They need to be able to understand, and they need to be able to be comforted that yes, this makes sense. Yes, I understand how you're going to refuel this. Yes, the risks are not as great as it's perceived to be. They need to be trained up to that level, and that's why we chose water reactors, because regulators are already familiar with this. Regulators are already familiar with off-the-shelf material. When if you pass the EPR fuel, that's the one that we're going to buy. We're not going to buy. We're not going to design a new fuel that you're not familiar with, that we have to train you to, so that you understand why this fuel is good and so on.
if you did have unlimited funding right now, for example, is there a way of predicting how long it would take to finish and get ready for the process?
That's a very interesting question. Now we think right now with reasonable funding, not unlimited funding, with a reasonable level of funding, it will take probably about 10 years
Yeah.
from receiving the funding to being able to build a full reactor, to the start of construction of a new reactor. So we think it's going to be finished in 2 or 3 years. So let's say 13 years from the date of funding to the date of the first electricity produced by this plant somewhere in the world.
Yeah.
But with unlimited funding, I suppose that there's a critical path in every project management. There's a critical path, like whatever amount of funding you have, you're still limited by the critical path.
That's true.
We think it'll be probably 4 to 5 years to concrete pouring, meaning if they complete in 3 years, so 8 years instead of 13 years.
So that's right. It does depend on the level of funding. Significant difference there. Yeah.
Yeah.
Okay. Well, very good. And so I want to thank you for that. Is there anything? Maybe we should try and wrap up. Anything you want to say to wrap up? And
Sure. Well, thank you for giving me this opportunity to share this
yeah,
design that we kind of developed in Imperial. It's something. Looking back, it's just like you said. Why haven't other people thought of it? And because to us at least, it's completely logical, and
yeah.
it makes sense, and it's just natural circulation. It's safe. But to me, I think it's just because the industry has been going the wrong way. They want to improve. They want to improve efficiency, and they want to improve safety together, and that's why uh, that that's why your capital costs have increased so far. And the problem is, once your capital costs increase up to above a certain point where huge utilities cannot afford your power plant, then what's the point of design of marketing your power plant in the first place? If you price it above what your customers could afford,
Yeah.
and so we want to do it the other way. We want so our reactors. You don't have to be a utility to buy. You could probably own a huge steel melting plant. You could build this reactor next to it and just get the power from this reactor. You don't. So that means the vendor of this reactor would not. The target market is not just utilities. It could be large power consumers as well.
So you're not promoting the thermal aspect. You're but if it could still be used for industrial purposes.
It could, but it will have to generate electricity first. At least this design is made for the grid. It's
Yeah.
made to generate electricity. If
Yeah.
we want to access the waste heat and use it, do it something useful for it, we could still do this, but it's not very efficient. It's not designed for that. This is designed for the grid. This is designed to produce electricity. You can produce hydrogen with this simple. If you have a plot of land and you build this reactor and just produce
Yeah,
hydrogen,
you're
you
kind
could.
of implying that some kind of microgrid might
Right.
it might be useful for that, right?
Yes, yes, yes.
Yeah.
There are some small model reactors. They sit in a area where you could power a large grid and you could also power a microgrid. There's a sweet spot
I
between.
was using the example of somewhere like Disneyland. If they wanted to power all of
Mm.
Disneyland with one of your reactors, they could probably do it.
They still have a lot of excess energy that they produce that they could sell to the grid because they still produce a lot of energy.
Yeah,
This
yeah.
reactor, even this
Okay.
one.
Or how about amusement park in the Arab Emirates?
Yeah, I suppose.
Okay.
Well, if they want to do that, if it's UAE, they have a lot of money. We'll design a different reactor just for them.
Okay, great. Oh, so
Yeah.
thanks. Yeah, that's wonderful, Azrudi, and I appreciate your time. And I can imagine easily at a later stage having another podcast with you. So that'd be
Oh,
great.
great.
So
Yeah, I'll be happy to come.
okay, so thanks very much, and we'll call it a day. And look forward to seeing your developments. Okay.
Yeah, thanks. Thank you.
Okay.
Thank you. Have a nice day.
Yeah. You too. Bye.
Bye.